Before we get into it, I do want to talk about just some general thoughts about the exam, some things that as teachers we do need to be aware of and are worth addressing with our students. The first thing, this was a change for the 2020 exam, but some staff and some teachers are still not quite aware of this. Just if students cross out work, that doesn't get marked. It used to get marked, but it no longer counts towards their mark. That brings maths into line with all the other subjects. So it's really worth hammering home to your students. If they want to cross out a piece of their work in the exam, they really should only do that after they have replaced it with something else that they know is correct, or at least a better form of correct. Students do get a little bit of grace in their answers. The purpose of the exam is to find out what students know. Now, sometimes students under pressure, maybe they swap out a negative sign, make it a positive or something kind of like that. And in some cases, that's not really part of the mark scheme, so they won't get penalised for that. However, if they do make one of those trivial errors, they need to be careful about a couple of things. Firstly, they can't make too many of them. Too many trivial errors is not trivial anymore. If work that continues on from there is vastly simplified from what is expected, then students won't be able to get all the marks for that subsequent part. Okay, usually if a student makes a mistake, if the next bit is done well, they've shown the right understanding and it's the right level of complexity, comparable, they'll get those follow-through marks, but they won't get follow-through if they've made it too easy for themselves. So students need to be aware and mindful of the number of marks allocated and the amount of space that's given to the questions. The other thing students need to be careful of if they make a trivial error, particularly if they're not aware of it, is if they get a result that just doesn't make sense. So for example, it could be a negative result where it only makes sense for there to be positive values. If a student gets to that point, they get that unreasonable result, they can rescue that mark by simply writing something along the lines of, that doesn't make sense, this answer should be positive, or whatever the situation is. Okay, so they don't necessarily need to go back and find that error and fix everything up. Of course, they probably should if they've got time, but certainly if they get a result that's unreasonable, they have to make a comment to rescue the final mark. I always encourage my students when they open up their exam, when they open up their tests, to look out for key words. The most important kind of word is a verb. The verbs are written specifically to tell the students what they need to do. Okay, so if a student can spot that verb, they can usually go from there and go, oh, that's what this question is about. So verbs are really important. Secondly, some of the key language. Using the word exact, some students just gloss over that word. Exact means it can't be a decimal. It needs to be something usually involving pi or exponential e or a logarithm or something like that. The word hence as well, students need to watch out for that. That means they have to use the previous result. And a lot of the time, that previous result is actually given to them. I really enjoy seeing through this exam a lot of examples where the questions, part A might be, show that this is one thing, and then the next part says, hence, do something with it. Okay, it's a very common sort of pattern that we're going to see a few times tonight. The final word that I think students need to watch out for is when we start talking about an algebraic process. I mean, it's obvious, isn't what students need to do there, but the number of ways that students answer that sort of problem without doing an algebraic process is, well, I'm sure you can understand. The final thing to be aware of is questions have lots of, hopefully, a number of multiple entry points. So if a student can't do part of a question, they need to keep looking at that question. They can't just go, oh, I got to part B, that was really difficult, I didn't get it, this is getting kind of weird, and then just go to the next question. They should actually be looking at the next part or a few parts after it, just to try and find that low-hanging fruit that they can come back in and start again in that question. So those are some general thoughts about the exam. Let's get into each of the questions. And let's see how we go. Question number 1, as I said at the start, was like a warm hug of a question. This is not a particularly imaginative question 1. It's basically, did you learn how to do calculus earlier this year? Nearly 2/3 of the students said yes, and in fact they got full marks. So this question is always done really, really well. A couple of things just to make sure you're reminding your students of. When it says there is no need to simplify your answers, there is no need to simplify your answers. They're wasting their time if they try and make it look pretty at this point. The markers aren't looking for pretty, simplified expressions. This question is just, can you do calculus, right? So just show that you can do the calculus. Question?
Yeah. What happens if they did the first bit and they got it all right, and then they went and tried to simplify it even though it said not to, and then they got something wrong?
So once students earn the mark, they can't unearn the mark, right? If a student, like let's talk about this question here, right? Doing a bit of the quotient rule there. If a student gets to this line here and goes, oh, there's a bunch of x's here, let's cancel those out. Well, they can, that's right. But then if they, cancel out one of these x's that they shouldn't, or they cancel to, they've done the right thing here. They've shown that they can use the quotient rule. What some students do in this question, though, is they turn it into a product rule. That's perfectly legitimate, but it does increase the error rate. So students who do turn this into a product rule question typically performed less well than those students that just went, quotient rule, let's do that. The other thing to be aware of as well, when we're looking at a chain rule, just this extra bit at the end, students tend to forget that. So as teachers, we really need to make sure that we're hammering that with our students. So question number 1.
Are they going to lose a mark if they don't put a bracket around it?
No,
Did they? Sorry.
Did they lose a mark if they didn't put brackets around that one? I don't know the answer to that off the top of my head.
Generally speaking, we're pretty forgiving with brackets.
Yeah.
At least really early on in the paper.
Yeah, and again, yeah.
You want to encourage your students to do it, right? Like it's silly
It's
not
terrible,
to.
maths not putting a bracket.
Yeah.
Absolutely.
It's an incorrect statement.
Yes,
So.
it is. Okay, cool.
But generally speaking, particularly at the beginning of the paper, you're really trying to look at rewarding students for demonstrating understanding. So like little things that Tim hasn't mentioned, for example, they replace the dy by dx with an f dash of x or something silly like that. That's also forgiven as well, right? Because they've shown the understanding of what they're trying to do in the paper.
Yep. Were there other, sorry, I'm actually having a little difficulty seeing, because I've got these lights here, and I just looked in them and I'm blind now. So just if I don't notice your hand, particularly this group up here, feel free to make a noise like a cough or a, something else, as long as you're nice about it. So question 1, a really straightforward question. Let's have a look at question number 2. Question number 2 starts off, here's a nice little polynomial function. Let's do a couple of things with this. Let's find some derivatives. Let's look at some properties. And students responded really well to this question. In fact, half of them got 6 out of 8 or more. That 6 out of 8, I think, has a little bit to do with the very final part of the question. We'll get there in a minute. The first part, finding the derivative, really straightforward. Part 2, using an algebraic process, determine the x and y coordinate. Again, this question is really, I think, well structured in terms of saying this is what we expect you to do here. But a couple of common errors that students made were going from x cubed is equal to 1. Some students went, oh, that means x can be plus or minus 1. So they confused that with an even power. The other common mistake that was seen was in this final step, taking that x is equal to 1 and substituting it. A bunch of students still substitute that into the derivative function. my advice to my students is if they are substituting the x-coordinate of the stationary point into a function and they get 0, they need to stop and think and just make sure, particularly when there's a graph that clearly indicates that it's not at 0. Over the page, B part 1, again, really straightforward, find a second derivative. Now we get into part 2, the first question that really started to test whether students actually knew what they were talking about. For lots of students, inflection points are where the second derivative is equal to 0, and that's true. But an inflection point more correctly is where the sign of the second derivative changes, when the shape of the graph changes from convex to concave. And in order to use mathematical reasoning, in order to determine whether there are any inflection points, students needed to, first of all, find when the second derivative was equal to 0, use a sign diagram or other similar reasoning along the lines of, say 24x squared will always be at least 0, right? That's also acceptable. So they need to talk about, it doesn't change sign, and then make a conclusion there. No, it doesn't have an inflection point. Students can't just rely on the graph. If you have a look at the graph, if you look at it quickly, it doesn't really look like it has an inflection point. It doesn't look like it changes shape, but we don't really know what's happening in this section here. And the graph, the scale is quite condensed. So maybe something could be going on there. We can't see that from the graph. We need to use the mathematics to get there. And that's question number 2. Any questions before we move on to question number 3?
So if they talk about there's no change in the shape, they get the mark. You don't need to mention that there's no sign change. So you have to actually say this, based on there is no change in sign. Can they just talk about the shape?
There needs to be some level of evidence, and that evidence needs to be something on the lines of the sign, or something like, talking about 24x squared. Does that make sense?
Yeah, I get the 24x squared, but I think by looking at the sign diagram, if they're inferring, they're looking at that saying there is no change in shape.
Yep.
Isn't that showing an understanding of the sign diagram?
If they have a sign diagram, it's probably okay.
Yeah.
If they don't have a sign diagram, they're just literally
Oh,
looking at the
no,
graph and
there's no
saying,
sign diagram.
Yeah.
Cool. Thank you.
All right, let's go to question 3. We are rocketing through the first few questions, just because I'm aware the latter part of the paper is where things are going to get a little interesting. Question 3 was the second best done question in the paper. In fact, half of students got full marks or 6 out of the 7. There was a little bit of complexity in the context given 3 here, but if students work through that, really the most important thing is we've got a mean and we've got a standard deviation. Those are the sorts of things I'm encouraging my students to watch out for and grab a highlighter and highlight at the start. State one reason why modelling V with a normal distribution would not be appropriate. When we are answering this question about normal distributions, we need to think about what our facts about normal distributions are. So for example, those 2 facts really are they're bell-shaped and they're symmetrical. The graph itself, if you look at it, if you squint, it could be symmetrical, kind of. It's definitely not bell-shaped though. So in terms of answering that question, they should be using that language about bell-shaped because that's probably the most accurate way that they can describe it. Yep.
If a student did say it was symmetric, would they get the mark there?
So if they said it was symmetric, that would be that's an argument for a normal distribution being appropriate. So I don't think they would earn that mark.
What about if it says not symmetric though?
If it's not symmetric, I don't remember off the top of my head. I think the key fact here is it's not bell-shaped.
yeah, I'm not sure. I can't remember off the top of my head, but the stronger answer is the whole idea of spell check.
Yeah.
Because
Yeah.
whether it's symmetrical or not is kind of a bit iffy, really.
What did they say, not normal?
Well, that's not really.
The question says not normal within it. When you use a definition to define something, it's in over grey.
Yep. All right, I have to apologise for part B. Clearly, I was half asleep when I wrote up these solutions. There is a mistake in the solutions. That 4 at the end of my answer should be a 2. I'd like to thank the person who pointed that out to me most generously in Tuesday's session. This sort of question is one that should be really familiar with the students. We've seen this sort of thing so many times in so many papers over so many years. Here's a couple of histograms. Which one is which and why? When students answer this question, they need to make an explicit choice. So explicitly choosing it's figure 4. And then their justification needs to be based on the numbers that they're seeing in front of them. They can't just wave a magic wand and say it's the central limit theorem, which I'll be honest is kind of what I really want to do. But there needs to be a little bit more evidence using the numbers that we've got. The central theorem states that as the sample size increases, the normality of the distribution, or it approaches a normal distribution. And because 10 is more than 2, we would expect this, the distribution from sample sizes of 10 to be a better approximation. You could also talk about the larger spread of values in figure 4, but be really, really careful about that. Just notice the difference in the scales that each of the diagrams have. So that's just something that a few students did answer there. In part C, the one thing that we keep coming back to, and I think we say this nearly every year, why is it reasonable to make an assumption that S of some really large number can be modeled by a normal distribution? If you look really closely in the Hayes textbook, which I understand most of us probably at least have a copy of, it talks about a rule of thumb, or actually a couple of rules of thumbs in different places. Those are a waste of time. We're not interested in them, right? What we're doing in this question, and all the questions of this type, they're comparative questions using values within the question itself, never to an external reference of, say, 30, for example, which a lot of students referred to. Some students did say something along the lines of n greater than 10, which is along the way towards saying 900 is greater than 10, but it just looks a little too close to a rule of thumb of n greater than 30. So students need to make sure that their answers are using the numbers in the question itself. The last 2 parts of this question, it was a nice coming down from what we've done in the central limit theorem here. These 2 parts are really, really straightforward. It's just plug into the formula, grab your calculator, do all the stuff you're supposed to do. Shall we move on to question 4? Since the course changed from Maths Studies to Maths Methods in 2017, this topic of logarithms and transformations was added to the course effectively in 2017. This is something I'm going to be blunt about. I don't think the Hayes textbook does very well at all, or even if at all, to be completely honest. But it is something that is within the subject outline, and it is something that is well worth helping your students to become familiar with. All of your students, as year 11s, probably started to explore trigonometric functions. I find that that is a really good base to jump off of to talk about transformations of logarithm functions. There's a lot of overlap. There's even a lot of similarity if we consider our general formula. If we write it kind of like that, that looks really similar to the general sine formula. And lots of things in the same area kind of behave the same way, right? So this B sitting in here is probably going to do a horizontal translation. The A here is probably going to do something about a horizontal dilation or a vertical translation. And that's where Lin kind of behaves a little differently to sine. And it's actually really interesting to explore that with your students, and I'd strongly encourage you to do so. Getting into the question itself, in terms of actually working through it, it was reasonably straightforward. Nearly every student, probably I think about 90% of students earned some marks in this question, and almost 50% of students got 5 or above, indicating a reasonable level of understanding here. Part A show that these derivatives are equal. To get this mark, students really needed to give that little bit there, right? Some of the show questions in this paper were really not asking very much of the students. They were really asking students to show something so that they could do something else later on. But because it wasn't asking for the students to do very much, there wasn't a lot of room for error or fudging within their answer. So yes, while a student could say Q dashed is equal to 1 on X and just write that, that's a true statement. They haven't shown why it's that though. And that's really what they needed to do in order to earn the second of these 2 marks here. When we get to describing the relationship between the graphs, this is my favourite solution, but there's a few other ones that you could potentially talk about. You could talk about what was the other one? Oh, the slopes of the tangents being the same for the same values of x. That's a relationship between the graphs. I just automatically go, we're talking Lin, we've got a couple here. Let's talk transformations, right? So a vertical translation. And I've given 3 Lin 3 units there, just in brackets, because I like that's a better answer, but just it's a vertical translation was enough. Heading on to the other side of the page here, we've now got a new function, r of x. We can see the graph in figure 6. Determining the values of a and b just required students to show that they know some of the log laws. Some students evidently didn't, and they took that log apart and wrote ln of x squared plus ln of 6x plus ln of 9, which made me want to faint. Determining the values of a and b, they didn't need to write a equals 2 and b equals 3. It's really obvious, right? If they put it in that form, that they know that a and b are those 2 values, right? They've done all the right things. They've done a couple of log law sorts of things in that part there. The final part, again, the language of transformations just comes through. It is really, really important when students are talking about transformations to include the direction, the kind of transformation it is, and a numerical value that quantifies how much. So we've got a horizontal translation of 3 units, and I've given a direction of left. You could maybe drop that word horizontal if you're in a rush, right? Left implies horizontal very strongly. Vertical dilation with a factor of 2. Okay, when we're talking the transformations, these are the sorts of language that we're going to use. That's question number 4. Shall we look at question 5? Wonderful. Question number 5. This again was a question done really well, or at least parts A through to D were. This question was the binomial distribution. This was discrete random variables. Students love this stuff, they eat it up. I know that for me, the last 5 years of teaching this, every time I've done this particular test, it's always been the best one done. There's still some really rich and complex things that students can do here. We're not really exploring those in here, or at least not in any great depth. The modal mark, so the most common mark for this question, was in fact 9 out of 9. A quarter of all students achieved that mark. The second highest frequency result was 6 out of 9, and 1 out of 6 students got that. And I think that's because of part E. So we're going to skip through most of this question because it's all reasonably straightforward. We'll talk briefly about D part 2, because this is an area where students still just muck up. It's an easy error for students to make. When the question's asking more than 5 guests, the students put in 5 as the lower boundary on their calculators and get the wrong answer. One thing I encourage my students to do, if they're working in a discrete distribution, rather than having the number in front of them be something that isn't in their distribution or isn't in the values we're interested in, so the 5, get the numbers that are actually the values that you're considering, right? So 6 and up. So I've turned that probability that y is greater than 5 into, it's the same as the probability that y is greater than or equal to 6. And that just means that I've stopped and I've thought and I've gone, 6 is what I put into my calculator, not 5. Of course, if you do go down that path, be really careful, because for continuous distributions, that relationship is not going to hold. Probably that y would be greater than 5 is the same as greater than or equal to 5 for a continuous distribution. So students do need to be careful when doing that. In part E, there were a few different approaches to giving an answer to this question. Personally, I prefer the one in black, just because it's a little bit friendlier, it's a little bit more fun, and honestly, it feels just a little wrong doing a trial and error approach in a maths methods exam, but it's legitimate. However, in order to get 3 marks for that question, using a trial and error approach, students need to show the 2 values immediately either side where it tips over from being correct to incorrect, or vice versa. So they have to show the probability when they are interviewing 37 guests, where it doesn't work, we get less than 0.9, and 38 guests, where our probability tips over into being above 0.9. Those are the first 2 marks. The third mark is just making a decision, right? Going, it has to be 38. Okay, even though it kind of looks a little obvious from, the fact that they calculated a 38, they need to explicitly say 38's the one, okay? The algebraic approach is a little bit more intense. They get rewarded later on through that process, just for equality's sake in terms of the processes. There's a few things they need to do there. They need to be familiar with this sort of notation, the binomial formula. They need to use some ln, so some log laws in here, and then obviously work towards getting the same answer. They're working with an inequality in here. It does make it a little bit more tricky as well. They also need to recognise dividing both sides by ln of 0.94, that's a negative number and it doesn't look like it. So they need to be really careful about that. That's question 5. Shall we keep going? Wonderful. Question 6. This is, I think, our first sort of real contextual question to the paper, or at least contextual calculus at least. So we've got some caffeine being drunk, just like I've got right here. I really liked this formula because it's a surge function, but it's not a surge function, but it looks like one. And it kind of works the same sort of way. I mean, you would expect drinking coffee, concentration in your blood, that's going to have that surge pattern. When students are asked to draw a graph in the exam, I tell my students that they should be cheering at that point because it's easy marks up for grabs as long as they do all the right things. Firstly, grabbing their calculator, plotting it on their calculator, making sure that they've got their axes set to be the same axes that we've got here. Then they can see it. As soon as they can see it, it's a little bit easier. Secondly, all of the critical points need to be roughly in the right spot. So for example, this graph goes through the origin, so their graph needs to go through the origin. It's got a maximum sort of up around here. I forget exactly what its coordinates are, but it's around about there. It needs to be, there. This graph has asymptotic behavior. They need to show that asymptotic behavior. And they also need to make sure that their graph covers the entire domain that is given to them. They can't just have their graph going, yeah, I've got that spot, and we're going to stop here, right? They need to fill the space as much as possible, okay? A couple of very straightforward questions here. This, as I kind of said earlier on, students need to consider the space and the number of marks. 1 mark, 4 lines of grid, grab your calculator, plug it in, get your answer, move on. All right, same business here in C Part 1. Grab your calculator. I mean, you can find the derivative, the value of the derivative just using your calculator. I know if you've got a Casio, you can do that. TIs probably do the same thing. You get the number, right, and you put it in there. Some students just really wanted to go, I need to find the derivative and then substitute. You don't need to do that. Calculators can do all that for us. When we get to C Part 2, this is where we need to really think about what this value means. And there are a number of facets to a really good answer here. And students needed to have enough of these to show they knew what they were talking about. The 3 key things were the fact that we're talking about after 2 hours, okay, it's C-2, not C-5. The units are actually kind of important, right? And that tells us it's 0.241 milligrams per litre per hour. Okay, it's an important part of the response. The final part is really using this word rate in context, talking about the concentration in blood plasma and, what it's doing. Okay, so there's a few different aspects to their answer. They didn't need to get all of them, but they needed to get most of them. Finally, moving through, we've got a show question, right? This is that show hence pattern. Showing this particular derivative has this form. It's a really easy one to do, so they need to make sure they're stepping it out very carefully. And then hence, so using what we've got up here, using what's given to them, show the concentration of caffeine in as blah, 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 etc. Okay, I'm going to introduce you to my favourite game. My favourite game that my students actually are very indifferent to, but they get over it. It's called Spot the Quadratic. This equation has a quadratic form. And if students can spot that it's got a quadratic form, then you can do quadratic kind of things to it, right? Notice how going from here to here, I've gone, that's the same as this business squared, right? It's just an index law I've used there. We've got that and that squared. We can pull out a common factor, and this is looking really very much like a quadratic. This business here, it's not going to be equal to 0, so we just focus on what's in the brackets, and now we're just doing some logarithm stuff. Okay, spot the quadratic. I highly recommend it. Your students will hate you for it.
It won't always be a quadratic though, will it?
Sorry?
It won't always be a quadratic.
No, it won't always be a quadratic. The reason why I get students to think about that is sometimes it is. And if it is, then it's a lot easier, it's a lot more familiar and friendly for the students to work with. But you're right, we're not always going to have friendly quadratics in this paper, which...
He's saying look for a common factor in the 2 terms.
You could do that as well.
Because there's a lot of different answers. I sort of went through this one.
Yeah.
You can add 4.5 to the 0.3t to both sides, and then there's lots of things you can do
Yep.
at the time. So I take your point. Yeah, they're not always going to be quadratics, right?
All right, over the page, this is the first 3-page question in the paper. Students really needed to make it very clear that we were going to get a maximum from here. So there needed to be some kind of reason for this value giving us a maximum when t is equal to t on 3 ln 2. So the first mark is just let's throw something into one of our equations we've played with previously. It could be this way. There was a couple of different ways that students could muck around with that. But then they needed to give some kind of evidence, not just going, it's always going to be a maximum at this point. They actually needed to, give some kind of information, because we are actually changing, we're talking about changing this value out the front here, right? And that could potentially turn it into a minimum or, something else. Probably a minimum, let's be honest, if it's a negative. So they needed to give some kind of evidence. I've given this kind of evidence here. It seems a little bit Mickey Mouse, to be honest, but it's evidence going, I've considered what I'm looking at here, and yes, I know this will be a maximum and not a minimum. Does that make sense? I'm going to assume by the silence that that's a yes. Okay.
So where are the marks there then?
I think 1 mark would be sort of roughly around about here, doing a substitution, and then another mark just down here. It doesn't need to necessarily look like what I've done, but some sort of indication that I've engaged with the fact that it might not be a maximum just by substituting. That is booklet number 1. Let's get into booklet number 2. So booklet number 2 starts off with what I'm calling the not first principles question, because it isn't first principles, but it's doing a couple of the chords and whatever else at the very start. Students do struggle a little bit. They're still not entirely familiar with what a chord is. It's really important that when you're doing first principles, I assume most of you probably already have, that you do use that language of chord versus tangent. I can see a few people nodding, going yes, which is wonderful. 2 marks for this part. They substitute that in. Yes, that is technically the slope, but it looks ugly. Let's make it a little bit nicer for that second mark through there. Over the page, B part 1. Lots of students actually found this quite challenging. Again, this was one of those questions in the paper where students needed to show something. In terms of showing what needed to be done here, it was really quite simple. Students were skipping steps, right? They weren't giving an exact, this leads to this leads to this. It was more like, we're at the start, oh, let's go straight to the finish, right? Not actually a lot to be done here. And then the same with the second part. Now, it seems a little strange having a couple of show questions, one after the other. These questions are here so that in the next part, students have got all the resources they need to be able to find a tangent. So they've got a derivative. This part here, we're getting towards this derivative here. We can then use that derivative to find the slope of the tangent, and then we throw that information into one of our tangent equations. It's really important to note that for the 3rd mark, students need to put the tangent equation into something that feels like a standard tangent equation, like y equals mx plus c or general form. And you can see those 2 forms given down here. Leaving it in this form, students really haven't done enough for 3 marks, right? They've found a derivative, they chucked a bunch of things in a formula. So that 3rd mark really needs to be, let's, make it a little bit more formal.
But shouldn't that be stated for the students? If you want it in general form or you want it in y equals mx plus c form, that should be stated. I mean, that is the rule at all points on that line of play. That's the equation of the tangent.
I absolutely agree with you. It's 3 marks though. Students, my advice to students is always 3 marks means 3 things.
It's not a guessing game. It's about maths. It's not about guessing how many marks when you get these marks. It should be clearly stated that that's what's wanted.
Okay. All right, let's head into question 8. Question 8 was a little bit of a divisive question. It started off really nice and friendly. Let's do some continuous random variables. And then we went into a conjecture. One of the things about conjectures is historically they've mostly been found in calculus questions, but it is certainly possible to do conjectures within statistics. And this is one example of a sort of thing you could do here. The first few parts, just a couple of statistics. About 10% of students got full marks, same proportion got no marks, and about a quarter of them got 8 out of 10. And I think that's coming into the last little bit where there is a conjecture to prove. The first few parts of this question are really straightforward. It's just do the things that we've shown you how to do, use the formula, use your calculator, move on, right? It's not particularly complex here. It gets complex when we get to the proving of the conjecture. I think a lot of students see the word conjecture and immediately panic. I've certainly had a number of students that have developed that sort of relationship with conjectures over the years. Maybe an aside. One of my fundamental axioms, I'm going to apologise, pure mathematicians, for the use of that word. One of my axioms of teaching is students want to be successful. And what students start to notice as they work through the middle school and into the senior school, they start to understand a little bit more about what it means to be mathematical, what it is that mathematicians do. And one of those things is they prove things. And so because students, they know that that's something that the mathematicians do, they know that that's something that, as their teacher, I'm probably going to respond positively to because it's being successful, right? From maybe year 9, year 10, in their investigations, I start seeing this idea of proof come in, right? They'll say, I've done this thing and this proves this. And invariably, they're wrong. It doesn't prove it, it just demonstrates it. But that is an excellent teaching opportunity when they're back all the way in year 9 and year 10, when they start bringing in this word proof to start teaching them. And you can approach that a couple of ways. I mean, you could just, speak to the student one-on-one, or you could actually, stop the class and say, hey, Dan's used the word proof here. Let's talk about what that means mathematically and how that might look and how that might work. So that's something that I try and do in my classes. I'd encourage you to do in yours, but I'd also encourage you to actually take back to your faculties as well. Particularly, in this room, we're all quite experienced mathematicians. We've probably all studied mathematics at university, or we've certainly come a long way in our mathematics or something like that. We're fully, trained maths teachers teaching in our field. Lots of maths teachers, particularly in the middle years, aren't. And so they wouldn't understand what that proof is. And so we have an opportunity to influence our faculties back in our schools to start thinking about that language. And I strongly encourage you to do so. In terms of proving the conjecture, look, it is actually a reasonably straightforward. Let's just grab our integral, do some integration things, do some substitution and get the answer out. It was acceptable to do a couple of different things. Students could, instead of having n up here, actually use this square root of m squared plus 1. If they use that and get everything out at the end that they should get, that's also adequate. They could even potentially use the a trapezium formula because, any shape here is going to be a trapezium, hopefully better drawn than that. Finally, over the page in this question, The one thing that students need to watch out for here is the language. Firstly, we're talking exact, so we're expecting a square root or a pi or something else. But students get hung up on this word, maximum. And they go, oh, let's do some differentiation now and make it equal to 0 and whatever else. It's quite similar. There was a question a couple of years ago. First principles involving an area of bacteria, and lots of students did integration at that point. So while we encourage students to look out for those main operator words like maximum or minimum or area, they really need to pay attention to the context of the question and what is actually being asked of them through this question. So there's something to watch out for there. That's question 8. This part of the paper is really about testing how far the students can actually take things. This question starts really nicely. We've got just a confidence interval there. It's a 99% confidence interval, so lots of students are used to 95%, but 99 is certainly something they should be able to do. The notation here, they need to make sure that that bit there is p, and not p hat, not x bar, not mu, nothing else, p only. The signs, so the inequality signs, they can have the equals bit, but they don't need the equals bit. It's equivalent. The really important thing is, have they got the two numbers, and are they saying that the population proportion is between those two? Part B, lots of students really struggled with this part. And this is why students found this to be the most difficult question. 50% of students got 3 marks or more for this particular question. It was a real distinguishing question for our students. This is how I approached it while I was writing the solutions. There are a few other options here that students could potentially use. My approach, and what I always ask my students when they're faced with something that looks really unfriendly, I started my year with my year 11s this year. I'd asked them to think about what is the most important question you can ask in maths. And we came up with some answers. My suggestion to them is it's not what should I do here, it's what's possible here. And I think a lot of students go, what am I supposed to do in this question? Which is a very closed way of thinking about things. Whereas if they're asking what's possible here, they're drawing a little bit more on the different things that they've come across here. And once again, my favourite game rears its ugly head. We can turn this into a quadratic. A couple of different ways. We can multiply out the square root, which you can see here. You can turn it into a difference of 2 squares by multiplying both sides of this line by p hat plus 2.58, etc. And that works out nicely. I guess what this question was really trying to do was ask the questions in the context of a stats part. How good is your algebra really? Okay, and that was distinguishing for a lot of students. This particular question, if you look at each question in most exams, they typically go from not as difficult to more difficult through each question. This question doesn't follow that pattern because it wouldn't make sense to flip around the last 2 parts. Students who struggled with part B had a really nice re-entry into part C, but a lot of students didn't take that re-entry, probably because they got to part B and went, this question's too hard. It's really important to emphasize with the students, find those re-entry points. This question here, we've got a formula. Hey, it's the same formula from yesterday. Do they understand p hat is x over 1,000? And then we're just doing a simple substitute, solve, and make sure we're talking about a whole number, rounding appropriately. They had to use the formula here. It explicitly said using the formula p hat is this. So students using trial and error weren't weren't able to get those full marks because it explicitly told them to use the formula. Any questions about question 9? All right, question 10. Now I'm just conscious of time. Is there another session after this? No. Okay, cool, I can go as long as I like. I won't. Question 10. Again, another one that just kind of took things in an unexpected direction. It started off really friendly, right? We know how to draw rectangles. It's a really friendly sort of thing to do. They firstly had to give an answer to some significant figures. They needed to make sure, obviously, paying attention how many significant figures to get there. Part B, notice there's no grid here. Lots of students skip out when there's no grid. Make sure you tell your students where are the marks, right? Don't look at the grid, look along the right-hand side, spot where it says 1 mark or 2 marks or whatever else. Now, this question's talking about rectangles. I'm hoping most of you received some information from the SACE board about the changes to the subject outline for this year. It is unfortunately a little difficult to find the actual subject on the SACE board website. It's not in the spot where it says subject outline, which is really frustrating. There's another bit underneath it. I was there today. Search around on the SACE board website for the 2022 subject outline. There have been quite a significant number of changes, nearly all of them just trying to make things a little bit clearer, make a little bit more sense, align things perhaps, where they should be aligned. One change that I've noticed directly relates to rectangles. Every time we've done this question in the past, it's always been on a function that is, or part of a function that is completely increasing or completely decreasing. That's no longer the case. Students from this year might be expected to find some rectangles for an upper estimate or a lower estimate on a graph with a maximum or a minimum. So please make sure you have a look into that, talk about it with your students, and make sure that you address that part when it comes up. I have enough opinions about the Hayes textbook way that they teach integration anyway. I won't impose those upon you. I think they misorder it. I don't think they do rectangles particularly well, so I always do that with my own stuff. This is something that I'll be encouraging the Year 12s at my school to make sure that they are across. Does that make sense to everyone? Are there any questions about that? Okay, let's get into the fun part. C part 2 part 1, says let's find a second derivative, right? It's going from like 0 to 100 straight away. Because normally it's like, find a first derivative first. But this function doesn't have a nice derivative, or at least it doesn't have a derivative that we can find without doing something like implicit differentiation, which, the spec kids know, but ours don't. What students needed to do here was recognise that if we've got a derivative of x to the power of x times ln x plus 1, and we know that the derivative of x to the power of x is x to the power of x times ln x plus 1, that's a product rule that students can use. So you can see here that I've set up, I like setting up my product rule like this. It seems a little bit, tedious, but it's a way of organising our thinking. And once that's organised, it's just let's plug it into the formula and we get our second derivative from there. Some students did make an unfortunate error. They did everything right except that ln of x plus 1, they treated it as ln of x plus 1, not ln of x plus 1, which was really disappointing. To show that this graph is always convex, for 2 marks, they needed to do a couple of things. The most important piece of information about graphs being convex is understanding that the second derivative is positive. Okay, hey look, there's a hence there, right? We're using what we've just done. We've said second derivative, you got to use the second derivative. And saying something about, yeah, it needs to be positive, that's part of the answer. But we can't just like say the second derivative is positive because, you know, that's a bit Mickey Mouse. We're showing this function is always positive. I think the best way of doing that is to break it into its parts, right? X to the power of x. If x is positive, it's always going to be positive. Ln of x plus 1 squared, it's always going to be positive. It'll be 0 once, that's okay. And then x to the power of x over x, so that's also going to be positive, you know, because the first one was as well. So giving some indication that, you know, each of the parts are going to be positive means that you know, we can justify that the second derivative is positive. And finally, hence, again, linking everything back, we're talking about the convexity, convexity of the function. That can be done really simply with a nice diagram here. You know, we've got our convex function here. Oh, look, that area of A is more than the area of B, so our underestimate is a better answer there. And that, I think, is question number 10.
Can I go back to II?
Yeah.
Were there other combinations in the exam markers that kids presented that warranted them 2 marks?
So
they may have not gone through your approach.
Yeah.
They have to go to that approach to get their full 2 marks.
I think that's a hard question to answer because you need to see the approach, right?
Yeah.
So like, if you could give me...
Okay, so if they found the double derivative, equated each part, showed there were no critical values on the sign diagram, did a sign diagram.
Can they solve those equations?
0
Not sure.
was positive, which clearly shows it's concave.
Stuff like that, like I can't say yes or no because I can't see that written down. You know what I mean? It's hard to sort of judge it, but like markers are generally sort of given the idea that if the student's trying to demonstrate evidence, if they demonstrate evidence, they'll try their best to see if they can give them a mark, and they probably would have flagged something like that for a supervisor marker to check through. Yeah.
Cool.
Final question. Question number 11, a tour de force through the maths methods curriculum. This question has everything. It's got some calculus, it's got some statistics, it's got some really hectic algebra. The median mark for this question was 8 out of 15. Less than 10% of students got 14 or higher out of the 15 marks. So it was quite a distinguishing question. Potentially, the marks were a little bit lower because this was at the end of the paper. Some students did struggle with time. But let's get into the responses themselves. So part A, we've got another confidence interval, this time for a mean. I've given my answer there of mu with the subscript of A because that's what the notation was. Just a mu by itself is fine, nothing else, right? We can't have P, we can't have X bar. It's indicating the population mean. Can the researcher's prediction be supported with a justification? I'm going to talk really briefly about evaluating claims because in a previous model, and I think this is what the Hayes textbook does. I like the Hayes textbook mostly, but I'm critical of it as well. A lot of the claims that are made are for singular values, right? So for example, the scientists here are predicting that the perceived completion time would be exactly 30 seconds, right? That's how that would be phrased under a former regime. Now, those sorts of claims can never be supported, right? If the claim is outside of the confidence interval, like it would be here, if it was, so the claim was 33, right? That's outside of the confidence interval, we reject it. A claim of 30 exactly, well, we can't reject it, but we also can't support it, right? It could be 30, but it could be anything between 27.7 and 30.7 at 95% confidence. The way that this question is structured, and this is in line with how confidence intervals have been constructed over a number of years is instead of the claim being a singular value, it's a range of values. When you have a range of values that you're making a claim for, you can sometimes support them, you can sometimes reject them, and sometimes you can neither support nor reject. So in this case, because there is some overlap, because the claimed area, let me organise my thinking. Because the confidence interval contains values that are not within the claimed set of values, right? There are values in our confidence interval less than 30, but the claim is that it'll be more than 30. We cannot support their claim. Okay, does that make sense? Whereas if the claimed value was that it would be less than 33 seconds, that's okay, because between 27.7 and 30.7 is less than 33 seconds. Okay? So there's there's a greater level of complexity possible when our claims are ranges of values rather than singular values. And that's something that students maybe don't get exposed to as much, particularly if you're using the Hayes textbook. Across the page in Part B, we see a situation where we can support a claim, right? There was a little spot in here where students did need to read very carefully. With the more than 10% longer, they needed to pick up on that to go, 33 seconds is what we're comparing. They're saying more than 33 seconds. The whole confidence interval is more than 33, so yeah, we support their particular claim. Heading down into Part C, this is very friendly at this point. It's just do some integration stuff. And then we get to the very final page of the exam. And this is where students are really having to work really hard, think very carefully. There's a couple of things just to be aware of here. Getting 3 marks for D Part 1 was really easy. What a lot of students didn't do was consider that because it's a periodic function, you get multiple solutions. They didn't consider all of those different solutions they could have and then go, well, none of those other ones make sense when k is more than 1, so it's just pi on 24. Okay?
There's lots of ways you could show it as well. There was like geometric arguments and things like that. So this was just one example of one possible solution.
The very final question, Part B. This was just some nasty integration. Really, students just needed to kind of keep track of what they were doing. There's a couple of tricks that students could use to make their life a little bit easier. Personally, I'm a fan of saying, well, we're trying to find out what this value of A is. That's a common factor. Let's pull it out the front of our integral. And then we're just dealing with this integration stuff without having extra parameters floating around. That's a bit friendlier. Because then it's just, do the standard integration stuff. Oh, there's an A out the front. And then let's divide by all of this. This question had a lot of various forms that were acceptable. As long as it wasn't a decimal, it was okay. One thing that students did do that was a little bit annoying was when they were back up here, they confused A for being a variable and tried to integrate that rather than integrating against T. Are there any questions about that?
Yeah, I've just got one, sorry.
Yep, that's okay.
Part C.
Yep.
It says write an interval expression for the percentage complete after 15 seconds.
Yep.
We had 4 maths teachers, and 2 of them interpreted that very differently. Went from 15 to 30 after 15 seconds.
Yep.
So 15 to 30, whereas some interpreted it to the first 15. So that was really interesting.
It's a tricky one to kind of word that because, naturally we talk, after the first 15 seconds or over 15 seconds, right?
Yeah,
but it doesn't say after.
It doesn't say first, it says after 15 seconds.
Yep.
So between 15 and 30,
No, that's a valid point.
That English was not correct.
Yeah.
I assume the markers would have picked that up.
I think so, yeah.
Did they accept it both?
I can't remember off the top of my head. But it would have, like this sort of stuff does go through a lot of editors, so
Oh,
I
yeah,
these are actually editors.
It's a question of tense, really.
It
Like,
is.
complete is current tense, so at the point of 15 seconds is current, whereas if it was completed after 15 seconds, complete is a bit more than 15.
Yeah, I think if you have completed, after.
Yeah, all kids would have picked it up.
Yeah,
Yeah, it's very subtle.
very subtle.
All right.
Can I say one thing?
Thank you.
Can I?
Yep.
Honestly, thank you so much for some of you guys asking questions. It's really important as well. So thank you again for asking a lot of questions. It's really good. Yeah. And thank you at the front as well. I'm up for the person that was at the front asking about the equation of a line. If you want to hang back after, I'll have a bit of a chat about it as well. That'd be cool. Yep.
Thank you all very much for coming out. Thank you for staying a little bit longer. Have an excellent rest of the evening. All the best for you and for your Year 12s this year.